Okay, so this video is still looking at 10E, consequences of the factor theorem, but what I want to have a look at here are the geometrical consequences of the factor theorem, or really the geometrical implications of the factor theorem. And there's 3 points here that we'll talk through, and then we'll have a look at an example, and then I'll get you to have a go at some in the exercises in the textbook. So the first one is saying that the graph of a polynomial function of degree n is completely determined by any n plus 1 points on the curve. So the example that I would like to choose to show you that first point there is this one down here. So if we're thinking of our polynomial p of x, and it's the quadratic x squared, and x squared passes through these 3 points, minus 1, 1, 0, 0, and 1, 1. So it passes through those 3 points. No other polynomial at all, except for x squared, passes through those 3 distinct points. So relating that back to our point 1, so if a graph of a polynomial of function n, and in this case our n is 2, is completely determined by n plus 1 points on the curve. So x squared is determined by 3 particular points, and these 3 particular points are 3 points that no other polynomial will pass through. So what that means, that for any other polynomial to pass through those 3 points, exactly, it would have to be identical to p of x. And that's what that first point is saying, and that gives us a little bit of an example about that. Now, the second point says, the graphs of 2 distinct polynomial functions cannot intersect in more points than the maximum of the 2 degrees. So here's an example that I'd use for 2. For example, if p of x is equal to x, so that's the line y equals x, and q of x is another polynomial, and that is x cubed, they will intersect at most 3 points. So relating that back to 2, it cannot intersect in more points than the maximum of the 2 degrees. Polynomial p of x has degree 1, polynomial q of x has degree 3. So there's 3 points that they can intersect at most. Sometimes when we've got 2 polynomials and we're looking at the maximum degree, sometimes it won't intersect at the value of the highest degree, but that is the most that it could intersect. And I'll quickly sketch these 2 for you to show that they do intersect at 3 points. So there's our x and y axes. Here's our first polynomial, y equals x, or p of x is equal to x, and we'll pop in x cubed in there, and that will look like that. So the 3 points that we're intersecting would be here, and here, and here. Okay, let's have a look at that third point there. A line cannot intersect the graph of a polynomial of degree n in more than n points. So for that third point, I think we could probably have a look at the polynomials that we've got down below here. So a line cannot intersect, and here we have a line, y equals x, cannot intersect a graph of the polynomial of degree n. So our degree n polynomial is x cubed, it is of degree 3. It cannot intersect that in more than n points. So the good example here is that we're intersecting a degree 3 polynomial at 3 points, and any other line that I was to draw with a positive gradient could not possibly intersect in more than 3 points. We might be able to go in 1 point. We might be lucky enough to get to 2 points, but there would never be 4 points because that's not going to be possible for us. So that's what those 3 are basically telling us. But I'd also like to have a look at an example that looks at subtracting one function of another and how that can help us determine what the graphs of 2 functions are going to look like. Okay, and this is the example here that I'd like to have a look at, and this will assist you in working through question 12 in the exercises. So we want to work through this one a little bit. Now it's asking us to factor the difference of polynomials. Now we learnt previously that if one polynomial p of x equals another polynomial q of x, then each part of each of those polynomials, or each coefficient of one, will be equal to the other. So if we were to subtract 2 identical polynomials, p of x and q of x, then this f of x here would be 0. So what we're assuming in this case is it's not 0, and we have 2 distinct polynomials. So the question is saying, by factoring the difference, f of x, and that's going to be equal to p of x minus q of x, we want to describe the interactions between the curves. P of x being here and q of x here. And we're going to find where p of x is above q of x. So we need to, I think, explain a little bit more what happens when we're factoring the difference. Okay, so before we get into actually answering this question, I want to have a think about why we'd actually bother to do something like this, p of x minus q of x. So I'm just going to move over here and have a think about that over here. So if I was to draw up some axes, my x and y axes, and we say we had a cubic function that's got 3 points of intersection on the axes and a quartic function. Let's just draw another one. 1, 2, 3, 4. So why would we actually bother looking at the difference of those two curves? Now, if I have a look at where these two functions intersect with each other, I've got a point there, one here, and one here. So they're intersecting at 4 different points. If I was to subtract one polynomial from the other, where these guys intersect, their y values would be 0. So if I was to subtract the y value of my cubic and the y value of my quartic, where they meet, one subtracted from the other is going to give me a value of 0. So by subtracting those two curves and finding my new function, which is going to be f of x, that new function actually tells me how many times my two curves intersect, because we're finding these points in here. We might write that up. The f of x tells us how many times and where p of x and q of x intersect. Okay, so this new function f of x that we're going to make in a second from the subtraction of p of x and q of x is going to tell us where and how many times the curves intersect. Because if we were to subtract the y values of each of those values, they're going to be the same at each of these points, because this is where they cross, so we're going to get that 0. So let's work out what the y values are going to give us 0 for over here. So p of x minus q of x. So I'm basically going to be writing my polynomial p of x. I'm going to take away q of x. Collecting like terms, I end up with this one. I end up with a cubic. So we're going to use our rules that we used before to factor it. So the factors of that cubic polynomial are going to be the factors of the constant term at the end. So we're going to have plus or minus 2 and plus or minus 1. And remember, I suggest when we're factoring those, let's pop in 1 and then minus 1 first. It's just because it's a lot easier to work with those values. So we're going to be looking for the factor theorem or the remainder theorem. In this case, we want 0 as our remainder. So let's pop 1 into our new function f of x. Remember, this is f of x here that we've just created. Popping 1 in gives us 1 cubed minus 3 plus 2, which is 0. So when we get via the factor theorem, when we substitute something in and we get a 0, we know that x minus what we've subbed in is a factor. Now, the easiest way to find the other factors is by long division still at this point. So if we do that, we're going to end up with x minus 1 times x squared plus x minus 2 is f of x. And I've written that down here again. So f of x is x minus 1, x squared plus x minus 2. And I can factorize this quadratic because we're really good at factorizing quadratics. And it factorizes out to x minus 1x plus 2. So what we actually have now are 2 lots of x minus 1 and 1 lot of x plus 2. So what that tells us is that our two curves, p of x and q of x, cross at x equals 1 and at x equals 2. And I probably should not use the word cross. I'm going to use the word meet at these points. They meet at those 2 points. And when we get a single point where they meet, a single point means that they cross each other. And this is where, when we have powers in here, the power of 2 is telling us that the two curves are going to meet, but they're going to meet at a tangent. Or we can think of them as they're going to meet and bounce away from each other again. So meet and bounce apart. So they basically meet at a tangent. I've written that a little bit neater at the bottom. So the curves P of x and Q of x cross at x equals minus 2 and meet but don't cross at x equals 1 as they are tangential. And that helps us helps us explain what's happening with curves without having to draw both curves. Now if we just go straight back up to the question and have a look what it actually wanted us to do, what it wanted us to do was find where P of x is above Q of x. So if we jump down to the down the bottom here, we might just quickly draw what we've got. So we know that we've got x is equal to minus 2 is a point where we're going to have a crossing. And we know that we're going to have x is equal to 1 is where it's going to bounce. It is a positive cubic, so we're going to look something like this. I don't have a value in here at this point, but I don't need that. So the question wanted us to look at where P of x is above Q of x, or P of x is greater than Q of x. So what that would mean is because we've subtracted our curves to find f of x, if P of x is above or P of x is greater than Q of x, we want to have a positive value. So P of x is going to be bigger than Q of x, so we're looking where f of x is positive. So where is f of x positive? It's going to be values of minus 2 and above. So for values of x is greater than minus 2, f of x is a positive value, and therefore P of x is going to be above or greater than Q of x. For values less than or equal to minus 2, it's going to be not above, it's going to be either equal to or smaller. We're going to get a negative number there. So hopefully that helps you out with that question, and it should help you understand question 12. So when you factor the difference, if we've got one single root, that's where they're going to cross. If we've got doubles or cubics, they're going to meet at tangents at that point. So they'll still touch, but they won't cross at that point, those two curves.